Hello everyone. The purpose of this video is to show you how to find slant or oblique asymptotes in a rational function. So what we've already talked about is how to find horizontal asymptotes. When the function is what we call bottom heavy, the exponent in the denominator is greater than the exponent in the numerator, we have a horizontal asymptote at y equals 0. Unless something gets added to it. So for example, if you had this term, plus 4, then it would be y equals 4. But failing that, bottom heavy, horizontal asymptotes at 0. It's kind of the easiest case. This exponent is bigger than this exponent, so your horizontal asymptote is at y equals 0. And the way you can think about that is that as x gets really large or really small, the denominator is going to increase or decrease much faster than the numerator, eventually approaching 0. Excuse me. So the second case that we've talked about is when the function is balanced. There's a horizontal asymptote where you would just divide the coefficients. So 3 over 4, excuse me, would be the horizontal asymptote, y equals 3 over 4. So that's a case where the exponents in the numerator and the leading exponent, the degree, is the same. 1, 1, 2, 2, 3, 3. If these are the same, the horizontal asymptote is the ratio of the leading coefficient. So here it would be 3 over 4. The last case that we haven't talked about yet is when the function is we call top heavy. That means the degree of the numerator is greater than the degree of the denominator. So that's what we're going to talk about today. And in this case, when it's top heavy, we don't have a horizontal asymptote. We have what's called a slant or oblique asymptote. They mean the same thing. And it's called slant because it's the equation of a line where the slope isn't 0. It's going to be slanted, and oblique kind of means the same thing as slanted. All right. So the question is, again, we're imagining we live in a world with no graphing technology. We don't have Desmos, we don't have TI-84s, we don't have anything. So how do we find it? Well, if you think about what we did here in bottom heavy and balanced, we're basically dividing to find what the function's going to approach. And that's the same situation here. We're dividing to see what the function's going to approach. So in Algebra 2, you did some work with polynomial long division. And that's what we're going to do with this. We're going to divide the numerator by the denominator. Okay, so to find the slant asymptote, you need to divide the numerator by the denominator. And I'm going to do a couple of examples here with you. So the first example will be this one. F of x equals x squared plus 3x plus 7 divided by x plus 4. So we're going to use long division to find what the quotient is, because the quotient, just like here and here, the quotient is going to represent your horizontal asymptote. And I'll show you what it looks like on the graph, even though we're not using graphing technology. I think it's instructive to look at what it looks like on the graph. Okay, so let's go ahead and start dividing. So you want to have everything in standard form, right? Descending order of exponents. So my dividend is going to be x squared plus 3x plus 7. And my divisor will be x plus 4. Okay. So the first thing I need to do is I need to divide. I'm just going to look at my my leading terms. I'm going to divide x squared by x. I'm going to ignore everything else, just x squared divided by x. That's just x, right? What times x gives you x squared? Just x. And where I'm going to put that is above the part of the dividend that has the same degree, right? 3x to the first, x to the first. Okay, so I'm dividing first. Now I'm going to multiply, just like you do in regular long division. I'm going to multiply x times x plus 4. So x times x will be x squared. X times 4 will be 4x. Okay. And now I'm going to subtract. So I'm subtracting this from this. So 7 minus 0, imagine this number is 0. 7 minus 0 is 7. 3x minus 4x is negative 1x. And then x squared minus x squared is 0, as it should be, because that's why we divided x into x squared in the first place. Okay, so right now, when we subtract, we have negative 1x plus 7. Okay, so now what we're going to do is divide again. So we're just going to look at this, the leading terms, right? Just like we did in the first step, we're going to divide the leading term by x. So negative 1x divided by x is negative 1. Then we'll multiply again. Negative 1 times x plus 4. So negative 1 times x is negative 1x. Negative 1 times 4 is negative 4. And then I will subtract again. So we're subtracting this entire expression from this. So 7 minus negative 4, 7 minus negative 4, that's 7 plus 4, or 11, positive 11. Excuse me, and then negative 1x minus negative 1x is 0, as it should be, because that's why we divided in the first place. So now, you would think, okay, well, I guess I divide again, right? I'm going, you know, purple, blue, green, right? Divide, multiply, subtract. But 11 is not really divisible by x, and you can't really get anything out of that, right? This is not the same degree. It's a constant. This is has a degree of 1. So you can't really do any more dividing. So what we're going to say is that we have a remainder here. We have a remainder that we can't really do any more work with. And that remainder is 11 divided by x plus 4, right? We would divide if we could, but there's nothing really that this will simplify to, okay? So now what we're thinking about, again, is this idea of the slant asymptote. If your x values start getting really, 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 really huge, what's going to happen to this remainder? If x is 1,000,000, the whole remainder would be 11 divided by 1,000,004. That's very, very, very small. So this is really going to kind of go to, this is going to get really tiny. I'm going to say this approaches 0. This remainder will approach 0. Approach 0. So it's going to become more and more insignificant. But the main quotient, what's in purple here, x minus 1, will stay relevant. It will stay relevant because you'll have 1,000,000 minus 1, 1,000,001 minus 1. This entire expression represents your slant asymptote. So for this problem, your slant asymptote is, or you can say oblique asymptote is y equals x minus 1. Okay. And now I said I was going to show you what it looks like on the graph. So I'm going to share screen for a little bit. So I'm going to just show you what the graph looks like. Okay. So you can see how it doesn't approach a horizontal asymptote, right? As your x values get very large, it looks like the graph is approaching a line, which is what the slant asymptote is, okay? And so what I will do, just so you can kind of see it, is I'll put a second equation in that is x minus 1, which is what we found. And I'm going to make it dotted, dashed, because again, it's not really a part of the graph. It's sort of a marker of what we're approaching. So that's the asymptote here. It's not a horizontal flat asymptote like, you know, the first two examples that we talked about in this video and what we were talking about last week. It's a line. It's the equation of a line with a slope that's not 0. It's a slant asymptote. So that's what the graph is approaching at in both directions. Okay. All right, let me stop sharing and I'll do one more example that's a little bit more challenging, but I think it's important to kind of show something a little bit different. Okay, so we'll do another example. So we'll say this was example 1, and here's example 2. So let's do one with a higher degree. So let's say we have x to the third. Well, let me write the function. So let's say the function is x to the third minus 2x squared plus 7x plus 6, all divided by x squared plus 3, say. Okay, so I'm going to divide the numerator by the denominator. So x to the third minus 2x squared plus 7x plus 6, all divided by x squared plus 3. Okay, so one of the things I mentioned is that it's important to have, when you do polynomial long division, it's important to have the exponents in descending order in standard form, 3, 2, 1, 0. This is in descending form, but we're missing, there's no x term, right? So if you want to think about this as x squared plus 0x plus 3, if that helps you, you can do that. Okay. I'm going to rewrite it like that just for instructive purposes, but you know, if you can do it without, that's also fine. It just helps me line up my terms. So we'll say this is x squared plus 0x plus 3. Okay. So I'm going to keep that same color coding that we did in example 1 here. So we're going to first just divide the leading terms. So x to the third divided by x squared. So x to the third divided by x squared is just x, right? So I'm going to put that above 7x because that's where I have my degree of 1. Okay, now I will multiply. Okay, so x times x squared would be x to the third. X times 0x is 0. I could say 0x squared, but it's 0. X times 3 would be 3x. And then there's nothing in the constant spot. All right, now I will subtract. So 6 minus 0 is 6. 7x minus 3x is 4x. Negative 2x squared minus 0x squared is negative 2x squared. And x to the third minus x to the third is 0. All right, let's divide again. So again, we're dividing the leading terms. Negative 2x squared divided by x squared, negative 2, right in that constant spot. Negative 2 times x squared. So now I'm multiplying. I'm going to change to blue. Negative 2 times x squared would be negative 2x squared. Excuse me. Negative 2 times 0x is 0x. Negative 2 times 3 is negative 6. All right. So now I need to subtract. So positive 6 minus negative 6 would be 12. Okay. 4x minus 0x would be 4x. And then negative 2x squared minus negative 2x squared is 0. Okay. All right, so now I'm at that point where I was at here. I can't really divide, so 4x divided by x squared is going to end up being really tiny. So once I have a degree here that is smaller than the degree here, just like we had 11 and x, we have 4x and x squared. So at this point, this is going to represent my remainder. My remainder is going to be 4x plus 12 divided by x squared plus 3. Because again, we think about it like we did here. This remainder is going to get closer to 0, just like our bottom heavy horizontal asymptote. As x values get extremely large and extremely small, this whole expression is going to be less and less relevant. It's going to approach 0. So I'm just going to write that here. You don't have to write that on your work, but I just want to show you why we're doing this, because the remainder will approach 0. So what that means is that I can stop here. My slant or oblique asymptote is y equals x minus 2. All right, and let me show you what that looks like again, just from a graphing perspective. So I'm going to share my screen, share the Desmo screen. So this is the function. This is what the function looks like. And you can see that it approaches an oblique asymptote. As you get farther and farther out, your graph is approaching a line. You can see that just visually. And now I'll put x minus 2 in next to it, and I'm going to make it a dashed line. So you can see it's not really a part of the graph. And as I zoom out, you can see that that is what the graph is getting closer and closer to. So as we zoom in, you can see it's not exactly aligned because of the remainder, right? But that's kind of where we're heading in both directions, because the farther out we go, the less and less the remainder is really going to matter, right? That 4x plus 12 divided by x squared plus 3 is going to be less and less relevant to what we're doing. Okay, so that is how you see it visually. And again, like I said, we're not really doing the graphing with technology right now. We're just finding it algebraically, but that is how you find your slant or oblique asymptotes. Okay, so I hope that was helpful, and I'll talk to you later.